All right. So that's time. Let's go ahead and take a look at what we got for these questions here for the warm-up. Starting with the first one, 5 squared. By the way, all of these should be done without a calculator. They're pretty easy to solve. So hopefully you guys weren't using that. But 5 squared is equal to what, Paulina? 25. Very good. This is equal to 25. Now, if I wanted to expand this, I could rewrite this as 5 times 5, which is equal to 25, right? All right, using that same idea, if I wanted to rewrite number 2, I would rewrite that as what times what? Josiah? What two things are getting multiplied in number 2? Very good. Negative 5 times negative 5, which is equal to what? Positive 25. Same answer. Great. Number 3, a little tricky. We are not using exponents around negative 5 anymore, so this might change our solution. Now, remember that we're doing PEMDAS, right? So first, before we have to do multiplication, we need to do the exponent. Now, what we're doing here is actually negative 5 times 5. So we're multiplying 5 times 5 first. Whatever we get, we multiply by a negative 1. So when we don't have parentheses, it does change our final answer. This is not negative 5 times negative 5. This is positive 5 times positive 5. Whatever you get, multiply by a negative 1. So our solution for number 3 should be negative 25. All right. Let's look at number 4. Rewrite the expression below as repeated addition. So what is 5 times 3? There's 2 ways to write this. If I'm doing 5 times 3, think about grouping. I have 5 groups of what? 5 groups of 3. Could do 3 plus 3 5 times. Which is equal to 15. Conversely, I could do a different set of grouping. What other kind of grouping could I do here? 3 groups of 5. Very good. So we could do 5 plus 5 plus 5. Either way, we get 15. All right, the idea here is that multiplication, though, represents repeated addition. Now, just like multiplication shows repeated addition, exponents now represent repeated multiplication. So 3 to the 4th power, we can rewrite as 3 times itself 4 times. In this case, is equal to 3 and 3 is 9, so 81. Okay. Very good. All right, so that concludes the warm-up. The main takeaway from this warm-up is to identify that exponents represent repeated multiplication. Okay. Now let's look at some guided notes. So please go to this section down below. And we are going to talk about the following rules. When it comes to exponents, we need to think of these rules, especially because we will be simplifying exponents. We will give you guys, equations that need to get simplified, and you're going to have to apply these rules to get a final solution. Now, one of the first rules that we're going to be looking at is the product rule. And the product rule works by multiplying the same base. So if you were to multiply the same base, what ends up happening is you would add the exponents. So, we see a very general example here with x to the a times x to the b is equal to x to the a plus b. Now, that's just the definition. I'm going to show you with an example how this works. So go ahead and write this down. Let's say I wanted to find the following solution to this problem. Let's say I had 2 to the 3rd power, and I was multiplying that with 2 to the 4th power. So go ahead and write this down. 2 to the 3rd power times 2 to the 4th power. Well, let's expand this. That's going to bring us some clarity here. 2 to the 3rd power, I can expand as the product of 2 times 2 times 2. And 2 to the 4th power, I can expand as the product of 2 times itself 4 times. Now, keep in mind, I am multiplying all of this together. Right? I have a group of 2 times itself 3 times and a group of 2 times itself 4 times. But altogether, everything is getting multiplied. So, all in all, how many times is 2 being multiplied by itself? Well, let's count it up. I have 1, 2, 3, 4, 5, 6, 7. 7 times that I have 2 written out. So I could actually rewrite this as 2 to the 7th power. 2 to the 7th power is how I could simplify this. Now, obviously, that's just me expanding this and then, just condensing it at the end. But how does the product rule work then? Well, it helps us to avoid, writing it out and then condensing it back together, because that would be too much work. Instead, what we can do is, since we have the same base, in this case, the base is a 2, then we can rewrite this as the sum of the exponents. 2 raised to the 3 plus 4 power. Once again, 2 raised to the 3 plus 4 power. What's 3 plus 4? 7. So we get 2 to the 7th power. Notice how we get the same solution for both of these approaches. The top way is utilizing the product rule. Okay? So keep that in mind. All right. Go ahead and try this example on your own now. We have 5 times 5 to the 3rd power. I want you guys to utilize the product rule to rewrite this. Go ahead and take 1 minute. All right, what do we get here then? Well, once again, we want to utilize the product rule. So we should be adding the exponents. Now, the first number, 5, do I see an exponent? Or in this case, do you guys see an exponent? No, but we can assume that there is an exponent. It's a 1. So in reality, we have 5 raised to the 1 plus 3 power. 1 plus 3. And what's 1 plus 3? 4. So we can actually rewrite this as 5 to the 4th power. Okay. 5 to the 4th power. All right. So once again, to summarize how the product rule works, when you multiply the same base, you add the exponents. Okay. Now let's see how quotient rule works. Now quotient rule is the opposite of product rule. Now we're not multiplying, now we're dividing. So you can kind of see here, general rule once again, x to the a divided by x to the b power is equal to x to the a minus b. So what do you recognize is different here? Are we adding the exponents? No, what are we doing now? Now we're subtracting. So when you multiply the same base, you add the exponents. When you divide the same base, now you subtract the exponents. So you do the opposite. Now, how does this work? Let's look at some of the reasoning behind this. And once again, in the reasoning is where I expand this to show you guys how it works. So let's say I wanted to find out 5 to the 4th divided by 5 to the 2nd power. 5 to the 4th over 5 to the 2nd. If I were to expand this, I would have 5 times 5, 4 times in the top, over 5 times 5 in the bottom. Now, remember that division, when you have the same number in the top and the bottom, it can cancel out. It reduces to 1, right? 5 divided by 5 is 1. So anytime I have the same number on top and bottom, I'm just going to draw a line through it to represent that this is now being reduced to 1. So that is a 1 right there, right? 5 over 5 is a 1. And this other pair of 5s also cancel out, or, equal to 1. So what am I left with? Well, I'm left with 5 times 5, which I can rewrite as 5 squared. Okay? 5 times 5 is equal to 5 squared. Now, if I were simply using the quotient rule logic here, this second step I could rewrite as 5 to the power of 4 minus 2, which gives me the same solution. Okay? I know it's hard to see. I can't zoom in anymore, so I apologize for that. But yeah, in both of these approaches, we get 5 to the second power. So here's your example. Ready? I would like you to try this next one on your own. 3 to the 7th power divided by 3 squared. All right. Do I have a volunteer who can help me out here? How can I rewrite this? 3 to the 7th over 3 to the 2nd power. Using the quotient rule, what would the solution be here? Yes. 3 to the power of 7 minus 2, which is equal to 3 to the 5th power. Excellent. Okay. Now keep in mind right now, I am not evaluating the exponents. I am not finding a final solution for 3 to the 5th power. All I'm doing is simplifying. That's what this review lesson is about. How do you simplify? That's what it is. You will get to a point where you might have to actually evaluate exponents. And I believe at that point, you might have access to a calculator. Unless the number's so small, then we'll just ask you to do it by hand. Okay, we have 3 more rules to cover. The third rule that you guys will see is the power rule. So what the power rule tells you is that a power raised to another power results in the exponents being multiplied together. So look at the example here. X to the a raised to the b power is equal to x to the a times b. All right? So let's look at an example here. How does this work? Well, let's say I had 4 squared and I was raising this to the 3rd power. So 4 squared raised to the 3rd power. Okay, so go ahead and write this down. 4 squared raised to the 3rd power. Now let's think logically here. Let's think about how we could expand this. We know that exponents are a way of showing repeated multiplication. 4 squared raised to the 3rd power could be rewritten as 4 squared times itself 3 times. Wouldn't you guys agree with that? Right? The base, in this case, the base that is getting raised to the 3rd power is 4 squared. So I would rewrite 4 squared 3 times. Are we okay with that? Okay. But we have some layering here because we have some exponents inside of what we just did. So we have 4 squared times itself 3 times, but we also have to rewrite the 4 squared. 4 squared is 4 times 4. So I could rewrite this then as 4 times 4 times 4 times 4 times 4 times 4. A total of how many times? This is 4 times itself, a total of how many times? Well, if you count them up, 1, 2, 3, 4, 5, 6, giving you a final solution of 4 to the 6th power. 4 to the 6th power. Now, this is the approach where we're expanding. If we just jumped straight into utilizing the power rule, we would have 4 to the 2 times 3 power, which is equal to 4 to the 6, giving us the same solution. Okay, so that's a little bit of the behind the scenes, but as you can see, when we utilize the rules, it saves us a lot of time because we're able to condense all of the work into just one simple step. Okay? Here is what you're going to work on now. Here's your example. Let's try 7 to the 4th squared. All right, let's take a look. So using the power rule, I would need to do what with these exponents? What would I need to do here? I would need to multiply them. So I could rewrite this as 7 raised to the 4 times 2 power, which is equal to 7 raised to the 8th power. Are there any questions on how the power rule works here? Okay. Let's go ahead and cover the remaining 2 rules, and then I will let you guys work on your Desmos for today. So here's the next one. The zero exponent rule. So this is the tricky one. Any number, no matter what number you have, but any number raised to the 0 power is always equal to 1. No matter what number it is. It could be 100,000. It could be -2. It could be 1.77777. Any number raised to the 0 power is equal to 1. Now, why is this the case? Well, let's take a look using the following example. Let's say I had 8 to the 3rd power over 8 to the 3rd power. Let me go ahead and expand this. 8 to the 3rd power is 8 times itself 3 times. So let's say I had that top and bottom. Now, don't forget, anytime you have the same number in the top and the bottom, it reduces to 1. So that's a 1, that's a 1, that's a 1. And in the end, I get a solution of 1. Now you might be wondering, well, this doesn't make sense. I don't see any 0 exponents here being applied. Well, not yet. But what if instead of the approach where I'm expanding the exponents, what if I just went directly to using the quotient rule? Well, 8 to the 3rd over 8 to the 3rd is the same as 8 to the 3 minus 3 power. And when I subtract 3 from 3, what do I get? 0. So I actually end up getting with, or I actually end up with 8 to the 0. But we know from the solution that we just got above, 8 to the 0 must equal 1. And that is how we get a solution of 1. Okay? All right. So try these next two. 10 to the 0 power. What's that equal to? 3 times 568 to the 0 power. What about that one? What's that equal to? So 10 to the 0 power is very easy. We just established that anything to the 0 power is 1. So 10 to the 0 is equal to 1. In the second example, we have 3 times some number to the 0 power. So 568 to the 0 power will equal 1. But you still have a 3 in front of it. So your final answer is actually supposed to be 3. So here are your two solutions. 10 to the 0 is 1. 3 times 568 to the 0 power is equal to 3. Okay? Are there any questions so far? Okay. Then let's finish up with one final example. Here it is. Negative exponent rule. X raised to the negative a power is equal to 1 over x to the a power. Or 1 over x to the negative a is equal to x to the positive a. How does this work? All right. Essentially here, by the way, the statement, or if I wanted to kind of explain how negative exponent rule works in a sentence, it would be when you have a negative exponent, whatever you have, you take its reciprocal. The reciprocal means you flip it. So if your negative exponent is a numerator, when you flip it, that now becomes the denominator, and vice versa. If your negative exponent is in the denominator, you bring it to the top. It becomes part of the numerator. So let me show you how it works, or at least the reasoning behind it. So let's say I wanted to do 9 to the 2nd power over 9 to the 4th power. Now, 9 to the 2nd over 9 to the 4th would be the same as 9 times 9 over 9 times 9 4 times in the bottom. Okay. Now, we've established that anytime we have the same number on top and bottom, it equals 1. So we would have 2 pairs of 9s that reduce to 1. But we also happen to have 2 pairs of 9s left over in the denominator. So we have 1 over 9 times 9, which we can go ahead and rewrite as 1 over 9 squared. So our final solution here is 1 over 9 squared, right? We get that from evaluating, or for simplifying, 9 squared over 9 to the 4th. Now that's just, once again, expanding, showing you guys kind of like behind the scenes. When I use the quotient rule is when you guys can really see this idea of the negative exponent rule. Because 9 to the 2nd over 9 to the 4th is the same as 9 to the 2nd minus 4. Now, 2 minus 4 is equal to negative 2. So 9 to the negative 2nd power is what I get. 9 to the negative 2nd power. But, once again, if you have a negative exponent, you cannot leave your answer like that. You just can't. It wouldn't be considered simplified. So instead what you do is you take the reciprocal. Currently 9 is a whole number, so we can assume that 9 is part of the numerator. 9 to the negative 2nd would become 1 over 9 to the 2nd, which is what we got above. Okay. Now, anytime you flip it, anytime you do that operation where you're bringing the top to the bottom or the bottom to the top, the exponent becomes positive when you do that. So notice how here the exponent was negative. When I brought it down, now the exponent is positive. So that's the only way that you can turn negative exponents into positive exponents. Okay. So here's your example. I'll give you 2 easy examples. Starting with the first one, 4 to the negative 2nd power. Give that a try. And once you're done with that, try this one, 2 over 5 to the negative 2nd. Second one's a little hard to see, but 2 over 5 to the negative 2nd power. So give the first one a try. I know some of you guys are still working, but I'll put up the solution for the first one. First example should be 1 over 4 squared. Now for the second one, it's a little tricky, but 5 to the negative 2nd, that is the denominator. To cancel that exponent, or to get rid of that negative exponent, I would need to bring it to the top. I would need to bring this to the top. So that becomes 5 to the 2nd times 2, which I guess if I were to evaluate this, I would get 25 times 2, which is equal to 50. Same thing with the top. If I wanted to evaluate the top, 1 over 16 would be my solution. Okay. All right, are there any questions on any of the rules that we've just covered? All right. So if there are no questions, then that concludes the guided notes.